back to the practical sizing. Right. So what am I doing here? Maybe let me derive. Last time we stopped here, right? But I did in a rush. But maybe I want to explain a little bit more. Now, so just think about what is the let me call this the derivation. Right. If what is the delay of an inverter? Right, practical sizing. Do you remember what we're talking about? We want to drive a very huge capacitor. Remember, very big cap, off-chip cap. Right. So if I want to minimize the delay, last time I showed you that it's going to take you maybe 2mm size transistor in order to minimize the output. Right? But your goal is that, right? Because this is the requirement from your customer. Your customer does not really ask you to minimize the output because he or she does not need that. They only want you to be able to deliver the signal within a certain requirement, which is TP maximum, right? So if that is the case, how should you build your inverter train, right? You know how to build your inverter train already if we are to achieve the minimum delay, right? But here we say that no, we just want to meet the delay, not the minimum delay, right? So we recall the delay of the inverter train of an inverter is TP0 times 1 plus F divided by gamma, right? TP0 is the intrinsic delay that we have learned before, right? If we assume gamma equal to 1, this is just approximation. In reality, you need to do simulation. Then, of course, this TP, it becomes TP0 plus F, right? Yeah. Okay. Now, then what is the total delay? So if use n stages, if I use n stages, okay, then the total delay is going to be, let me call it T, equals to be n TP0 times 1 plus F, right? If I assume every, I try to design it so every stage has the same delay. Is that okay? Now this n, like, if we want to satisfy the customer's requirement, right? We want it to have TP maximum larger than T, correct? Right? We need to make it so it's larger than T. So basically, it is saying what? Which is equal to n TP0 times 1F, right? So basically, it's saying we need to have T P max divided by n, not n, divided by TP0 larger than n times 1 plus F. Is that okay? Yeah, but what is F? Someone tell me what is F again, if I have n stages. Do you remember? What is small f? In terms of capital F. Yeah, small f is fan out of each stage. They need to be the same, right? But so in terms of n stages, how do you represent it? What's the relationship between the capital F and the small f? It's 1 over n, right? Yeah, because this is from here to here is F, here to here is F, here to here is F. So capital F equal to F to the power n, right? So if we assume this number is large, it's approximately e to F to the power n, okay? And that's how we get this equation. And then you can prove that they are the same. you also have this one. Okay. Now, so you don't need to prove it, but this is given. What I'm trying to say is that, remember, what is the scenario? The scenario is I want to drive a very large loading off chip. Off chip is usually large. How do I design it so that it just meets the requirement? Right? I don't need to have minimum delay, remember, right? Because that's not requirement. So I need to make sure my total delay is less than TP max. And then you find that in order to do that, your TP max divided by TP0 has to be larger than n times F1 over n. Okay, so you can do some optimization, right? But here show you the figure. This one, you call it TP, is actually TP max divided by TP0, right? For example, and then here is the number of stages. For example, if F is 10,000, if you use one stage, then your TP max divided by TP0 is 10,000, right? If you try to reduce the number of stage, increase the number of stage, then the delay will reduce. And actually, I say something. This is not TP max. TP max is the requirement. I'm sorry. This I'm wrong, right? This one TP here is the delay, the real delay. Okay, so you want TP divided by TP0 smaller than TP max divided by TP0. Okay, so here this graph tells you that what delay you will get for a given total fan out and different number of stages. Any questions? Maybe this is confusing. The best way is let's try to use it, right? We don't use this equation. You can use this equation, but now we use this graph. If the TP max is 2 nanoseconds, what does it mean? Customer wants the signal, right, to be less than 2 nanoseconds. You need to derive the signal in 2 nanoseconds. Okay, and the F is 8,000, right? And TI here, TI basically is T, which is just TP0, right? Is 30 picosecond, right? So how should we design our inverter tray? Okay, so first of all, what is T max divided by TP0? This is 2 nanoseconds divided by 30 picosecond, right? This is about 67. So we need, so the customer's requirement is that the delay is about 60 times of the intrinsic delay we have. So we need to find the make the TP divided by TP0 smaller than 67. Okay, so let's count. This is 10, 20, 30, 40, 50, 60, 70. So 67 is around here, right? This is about 67. We need to find a solution so that the delay is less than 67, okay? But it also depends on the F, right? If the F is 10,000, we read this curve. If the F is 1,000, we read this curve. Now, which curve will you pick? There's no 8,000, right? So we pick something, we assume it is 10,000 because this is larger, is a worst case for that. And you see that this 9, if F equal to 10,000, pick N equal to 3, right? Because when it is free, we get a delay less than 67, right? Because the delay is below this point. correct? So because of that, even we don't have 8,000, so n equal to 3 is good for f equal to 8,000. Is that clear? So basically here we say that we are going to design 1, 2, 3 stages to drive the load. This is the this is a big load. I don't know what it is, maybe 8,000. This is as a unit of 1, right? So what should be the size of this one? If this is 1, this is 8,000. What is the size of the second stage? Anyone? Firstly, tell me what is the, it's not working.
It's 8,000 raised to 1 by 3.
Good. Firstly, can you tell, thank you, right? We say F equal to 8,000. So small f is 8,000 to the power 1 over n, but we pick n equal to 3, right? So this is 8,000 raised to 1 over 3. Okay, and what is the number? Is 20. Okay, then can you tell me what is the size of this buffer if the previous state is 20? Now, this is very important, right? You need to know, even I did not teach you this slide. I just give you the number. I did not ask you to optimize it. I just give you the number. You should have already.
400.
400, thank you. Right. So I need 400, maybe micron, right? Still large, but which is less than the 2,000 micron we did earlier. Okay. So this is not a very good example, but the point is that you don't over design, right? When the customer asks for 2 nanosecond delay, don't go back to, oh, I need to minimize the delay. You don't need to. You only need to meet the criteria plus the variation. Okay. Any questions? Let's just pause for half minutes. Any questions?
Yes, Professor. Can you explain again why we chose n equal to 3?
Why we choose n equal to 3? First of all, here it gives us the delay of if you have different stages or for given f. So in our case, we look at f equal to 10,000 curve because it's close to 8,000 and it's just above 8,000. And then we say that the requirement of the customer is TP max divided by TP0 equal to 47, right? That is the requirement. We need to make sure the delay is less to it. This is the delay. We need to make sure the delay is less to it. So it means any curve that is below this 67 will meet the customer's requirement. But we are not going to increase it because it spends more area and also it is going to increase the size. So we choose the delay that just meets the requirement. If we choose, this is 2. If we choose 2, then the delay will be too much. Choose 3, it's just okay. If you choose 4, then you have very short delay, but that is over engineering. That's why we choose 3. Is that okay?
Yes, thank you.
Very good. Okay, let me move forward if you're okay, right? So we have been trying to understand how to optimize the delay, but how about area and power, right? How would the area and power looks like, right? What we are trying to do is just to come up some equation and then we understand why, how to optimize them, right? So if I have an inverter train like this, which is related to what I just asked you, right? Then you have a very big one. Then you go to the C low, right? And this one may have the minimum area, the first one, okay? And this is, and the fan, let's assume the fan out, right? Assume F as the fan out. We assume we already size it so that they have minimum delay. Assume as the fan out of each stage, right? Can you tell me what is the area of this one, of the second stage? If this is A minimum, the fan out is small f, then what is the area of this one? What is the meaning of fan out again? Right, so the concept, right? Some of them I keep repeating is very important because you can get lost very fast. You learn so many things, but then you step back, step on the ground. What is the definition of fan out? Ask yourself again. It is the output capacitance divided by the input capacitance, right? Then it depends on the area capacitance. No matter what you're talking about, C, DS, or the drain capacitance, the gate capacitance, it's a lump sum of capacitance, linear or whatever. They all are just like a similar triangle we learned in high school or middle school. Remember the similarity. They are similar to each other. Okay. How is the area related to capacitance? They are linear. It's just a similar triangle. If you remember from high school, if the edge have a ratio of F, then their perimeter also have ratio of F, because all these transistors is just similar to each other mathematically, right? So if the fan out is F, means the capacitance output of this capacitor is the input of the next stage, right? So if their input capacitance ratio is F, their area must be F, because capacitance is proportional to F. So this is F times A mean. Is this part okay? Then what is the area of the next stage? When I say that the fan out is constant throughout every stage, which is small f, what's the area of the next stage?
F square into A minimum.
F2, thank you. Yeah, thanks for I guess many of you know also, if that's the case, that is good, right? Or if you have any question, do ask, right? Don't wait until the exam is almost there. Just learn it now, right? So you go all the way and you have n stages. The last one I'm going to give you the answer is n to f to the power n, right? Because you have n stages. So you start off f0, f1, f2 to f to the power n. Okay. What is the total area of this circuit? It's just approximation. It's going to be A mean plus F A mean plus all the way to F n minus 1 A mean, which is equal to the A mean times 1 plus F squared plus all the way to Fn minus 1, right? And then the rest is just geometric series, right? So it becomes A mean times 1 minus F. We have n term. So this is just the equation. Okay. And what is F to the power n? Well, capital F. So the total area that you're going to use is 1 minus capital F minus 1 times 1 minus small f. That's it. Okay. This is just the equation. So it means in your mind, when you do the area optimization, right, you don't need that in this project, but in the future, at least you can think about this, right? the computer can help you to do many things, but this gives you a guidance, right? This one has no routing, it has nothing, but you just say that it will go up as A mean times 1 minus F, or F minus 1. Okay, any questions regarding the total area of the buffer? How about the power consumption? Right, what we care is the dynamic power consumption. What is the equation for power consumption? Do you remember for dynamic power that we learned already?
CL into VDD square into frequency.
Very good. C F VDD square, right? But we're talking about the total. Then you need to add them together, summation I for each state, CI, F, frequency should be the same, VDD are the same. Okay, so allow, then now it start making things complicated, right? So instead of small f, let me do period 1 over t. So you won't get confused later when you study. Okay, so this is basically VDD square divided by capital T, summation I, CI, right? But what is CI? CI proportional to area, right? And area again proportional to the depends on the stage, right? So this is nothing but just C mean F to the power I. And let me be clear now, what is I? We start from 0 to n minus 1, right? Because for the first stage, the capacitance is C mean. Okay, and then of course I is 0, so this is C mean, right? So this is the power consumption, right? So again, you get this equation, VDD squared divided by T times C mean, and then summation Fi is just the same as what we had before, 1 over F divided 1 plus F. Okay, now I'm going to do some approximation. This is VDD squared C mean divided by T. I'm write it as F minus 1, so it's easier for you to see. This is 1 minus F, right? I just swap the sign. If I assume F is much larger than 1, then of course, usually that is the case, right? We're talking about 8,000 just now, right? Then this is VDD squared C mean times capital F divided by T times F minus 1. But what is C mean times capital F? What's C mean times capital F? Do you recognize this term? C mean is the capacitance of the first stage, and capital F is the total fan out. So what is C mean times capital F?
CL.
Just CL, right? So it is just CL VDD squared divided by T times F minus 1. Hey, so you see that this is easy to memorize. The loading is just the CL VDD times T, which is just the power if you only have this CL loading. But because of this inverter chain, you also have F minus 1 at the bottom as the total power. Okay, so this is very important in the sense that you have some analytical equation, right? You know how to optimize the shortest path already. And then you also learn how to meet the constraint so you have a smaller area. We still all assume they have the same F. And then for the given N, given F, you then have the equation for the area and also the power consumption, right? So you can work out, for example, multiply them together becomes a power times area product, right? You can all do this in MATLAB and then optimize it to get some insight. And then you verify in the computer. Okay. Is this clear? Any questions? Okay, if no, then we basically finish the optimization. Now we want to talk about some issue about interconnect, which is very important nowadays. Let me remind you again at the beginning of